In this video, we'll be discussing some of the foundational concepts underlying inferential statistics. This one may be one of the longer ones of this lecture set, so just a heads up to be ready. One of the biggest components that relate to most inferential statistics that we use is the central limit theorem. The central limit theorem describes the distribution of what the population means look like, no matter what the individual data themselves look like. At the front, I'll note how this can be misused, and hopefully this will be a recurring theme through this lecture video, because I do want to highlight the potential for doing this incorrectly. We can use it to study group averages and means, but the central limit theorem is not applicable for individual data values. Ultimately, and we'll discuss what it says later, it simply says that when we look at a mean, the mean follows a particular distribution. But because we're looking at group means, that automatically discounts looking at individual data through this lens. I should call out that this is a serious limitation and frankly an often misunderstood one. A lot of people get this wrong for some reason. But even so, it doesn't remove the utility of the central limit theorem. There are many applications where we are trying to study group averages or average group movement rather than every individual's data. So for instance, if I'm implementing a drug trial or wait times in an emergency department, or if I'm looking to determine staff pay or anything like that, often I want to do average rankings and see on average is the wait time decreased or on average is the drug effective. These studies of group averages can be extraordinarily insightful, but it is important to acknowledge and understand this limitation so that when we are in a context where we want to study individual data, we reach for appropriate methods that are not going to be discussed in this lecture set. So to start, we'll need a little bit of background before we can fully address how to use the central limit theorem. We're going to start by learning a bit more about this very common distribution called the normal distribution. After we work through this and the rest of the things in most of this lecture video, we're going to circle back around to that central limit theorem and see how it all ties together. Now, the normal distribution is a bit of a misnomer because there are actually many normal distributions. In fact, there's an infinite amount of normal distributions. Normal distributions, roughly speaking, describe the specific shape of the distribution, sometimes called a bell curve. There are two things that make one curve different than another, and they are two of the major things that we discussed in the last lecture set. That is the center and the spread. So in this case, you'll see mu represented on this graph, which is a measure of center. It's the mean, population mean, and you'll see sigma squared represented on this graph, which is a measure of spread. And it is the population variance. Now, every mean and variance relate to a different normal distribution. The mean relates to where the middle of the normal distribution is, and the variance relates to how flattened or spread out the normal distribution is. You can see when the variance is small, such as in the blue normal distribution, the distribution has a higher peak and is much skinnier versus in the gold distribution or yellow, depending on how it's showing on your screen, or brown even, it is much flatter and more spread out. Now, the normal distribution has an equation which is associated with it. This equation is relatively complex, I think you can see, and ultimately has two components, the mean and standard deviation, that relate to, again, that center and that spread of the distribution. The rest of these components, pi and e, are constants, and x just refers to where along the distribution you are, left to right. So it is something that is present for everything, and it's just indicating where along the distribution you are. This would indicate the height at that point, and again, mu and sigma, changing mu and sigma give you a different curve within each. Now, when we say a variable is normally distributed, we tend to express it in this way. X being the variable that we're talking about, could be age, could be weight, is distributed normally with a mean of mu and a standard deviation of sigma squared. Now, sometimes we'll just plug numbers into here to say, hey, the mean is 30 and the standard, or the variance, excuse me, not standard deviation, sigma squared is a variance. The variance is 55. So we'll just plug numbers into these locations when we're speaking about them specifically. But generically, we'll just kind of use placeholders as mu for the mean and sigma squared for the variance. Now, this notation is important because it helps us to describe which of the normal distributions you're talking about. And remember, there's a whole bunch of them. So when we're talking about a normal distribution, one question is which one? Now, to help answer this question and to get all of these normal distributions on the same scale, we can go through a process called standardization. Standardization is actually broader than just the normal distribution. We can do this with any value, but with the normal distribution, and any value, we subtract the mean from each value and then divide by the standard deviation from that data. So the equation here looks like this. Z equals x minus mu divided by sigma. And again, the steps: subtract the mean, divide by the standard deviation, and this is the standardization. The result of this formula is the number of standard deviations from the mean, with a negative number indicating that the number of standard deviations is below the mean, while positive would represent that it's above the mean. So for example, if we got the results of 1.3, that would indicate that the particular data value is 1.3 standard deviations above the mean, while a result of negative 0.6 would indicate that the value is 0.6 standard deviations above or below the mean. So here, again, units are the number of standard deviations. And if you did this for all of the values in the data set, you would transform that data set to be completely standardized. If you did this for all values from a normal distribution, you would get the standard normal distribution. The standard normal distribution is one with a mean of 0 and a variance of 1. So recall earlier we mentioned we just put numbers in those blanks. Well, here I put the number 0 in for the mean and the number 1 in for the variance. Or maybe I can write this out here. Mean and variance. Ooh, it's tough to write with a mouse, so you'll have to forgive me. That's as close as I can get. Sorry, team. There's another distribution that we will occasionally run into that is often more appropriate, but is slightly more complex. And so I'll skim over it mostly in this class, called the T-distribution. All it is a type of normal distribution that accounts for additional error when we estimate variance from the sample. We'll need an additional piece of information called degrees of freedom. And degrees of freedom is just by default the sample size minus 1, though it'll change with different methods, and we can discuss the changes. Again, we won't touch it much in class. The T-distribution and the standard normal distribution are practically the same thing above n equals 30, so when we have big sample sizes. And below that, above that, it doesn't really have much of a return. And below that, we can't use some of the methods we're going to talk about anyway. All right, so note that the first step of the formula, that is this x minus mu part, this step is called centering. and can really help with some interpretation of statistical estimates in certain analyses. Ultimately, this allows the data to vary as they are, so vary normally, but it moves the middle of the data to be at the mean. So if my data originally ran from, let's say, 10 to 20, now the middle of the data, and the mean is 15, now the middle of the data, 15, is going to be the new center, and it's going to move down to 0. So now my data will vary from -5 to 5. This is a useful general practice because having 0 represent the mean of the data can, while keeping each data value's distance from the mean, and that's what the data value represents, negative values being values below the mean, can be, again, very helpful for interpretation with some statistical analyses. So this is something that we're not going to talk about more in this lecture set, but is something to file away for the future. All right, sampling distributions. So think through something that we kind of mentioned earlier. If we take multiple samples of 100 individuals from the population, let's say we had all the population values and we randomly selected 100 people from them, and we calculated a statistic from it. Well, I'll use the mean a lot, but throughout this lecture set, when you hear me say mean, understand that most of the time that could be any statistic. So it could be variance, it could be range, it could be interquartile range. So understand that that's more generic, but I'll use the mean because I think it helps intuitively. So I took 100 people. Let's say I'm calculating average height. 100 people, calculate the height, and it's a random sample from the United States. Let's say I took a different group of 100 people and I calculated the average height. The heights from those two random samples of the population are not going to be the same as each other, right? And if this doesn't make sense to you, maybe use smaller numbers than 100. Say you took a sample of 2 people, randomly sampled from the population, you calculate their mean, and then another 2, and you calculate their mean. Those clearly aren't going to be the same. Now let's say you do 3 and 4 and 5 and 6. Now they may get closer and closer together, but they're, as the sample size increases, but they're not going to be exactly the same. Certainly not down to the 10,000th of a decimal place, because we're going to very likely have different people in each of the groups. Now, it might average out to be the same, but they're not going to be exactly the same as each other if we took different samples. Okay, so if we can admit this to ourselves, I want you to play a little mind experiment with me. Let's say we did this a bunch of times. We got a group of 100 people, calculated the mean. Got a second group of 100 people, calculated the mean. Got a third group of 100 people, calculated the mean. Got a fourth group of 100 people, calculated the mean. Got a fifth group of 100 people, calculated the mean, and so on and so forth. Right now I have 5 means, but let's say I just keep doing this over and over and over again. What I could do is take each of those means that represents the mean of a group of 100 people, and I could put them all on a graph, and they would make their own distribution. This new distribution, based on the means from each of the samples, is called the sampling distribution of the mean. And again, I use mean here because that's how we're going to use this in a second, but we can do a sampling distribution for any statistic. We would just take a bunch of samples, calculate that calculation for each of the samples, and then put it on a graph. And that's the sampling distribution of whatever calculation we did. You could make up your own thing and create a sampling distribution of that thing. So this concept of a sampling distribution, we'll talk about more in a second, but understand what that is. That is, again, taking a group of 100 people, calculating the mean, taking a second group of 100 people, calculating the mean, and we already admitted to ourselves that those two are going to be different. Taking a third group of 100 people, calculating the mean, again, it's going to be different. And after we do this a bunch of times, with a bunch of groups of 100 people, we're going to get a bunch of means that represent each one representing the mean of a group of 100 people. And then we're going to put all of those means on a graph, and that's going to be this sampling distribution. This new sampling distribution of the mean is going to have its own mean. We'll call it mu sub x bar. That stands for the mean of the sample means. It'll have its own variance, sigma squared sub x bar, the variance of the sample means, and its own standard deviation, sigma sub x bar. That's the variance, or excuse me, standard deviation of the sampling means. It's worth noting the standard deviation of the sampling distribution is sometimes called the standard error. And all that this represents is the variability of what we were talking about with the first bullet point. That is, if I take multiple different samples of the same size from the population and I calculate the mean, those aren't going to be the same thing. So what is the variability of those different means? Again, they're not the same. What's the variability of them? That's this standard error thing. The standard error, sometimes called standard error of the mean. But this standard deviation of this sampling distribution, or standard deviation of the mean, again, we'll call it standard error. That is just saying how variable are these different means from one another if we redid this, take 100, calculate the mean, take 100, calculate the mean. Okay. All right, so I'm introducing this concept. This seems a bit weird and it seems a bit abstract, but I'm introducing it because we use this to answer a different question. So we use the individual distribution. That is the distribution of how our raw data, all of the individuals' heights, we use that to answer questions about individuals. We use this sampling distribution to answer questions about group means. Now, again, the individual distribution, that's how individuals look. The sampling distribution is how means look, specifically means of those groups of size 100. So individual distributions, we talk about individuals. Sampling distributions, we talk about samples. And in this case, the sampling distribution of the mean, we talk about group means. So if I have a question about individuals, I'll use the individual distribution. If I have a question about the group mean, I'll use the sampling distribution. And so that's the distinction here. Now, I'm going to give you a bit of a spoiler. It is very difficult to use individual distributions because we tend to not know what individual distributions look like. That is very difficult. I think I mentioned in the last lecture video in this lecture set that we kind of make up a distribution and it seems very arbitrary. And if we're talking about individual distributions, that is very true. Right now, we're about to talk about some math that allows us to understand what sampling distributions look like mathematically, with mathematical accuracy and precision. So we know what sampling distributions look like, and we're about to demonstrate how we know that in a second. But because of this, individual distributions, we tend to not know what those are. And so that's why we don't really answer questions about individuals. We, in statistics, in inferential statistics specifically, tend to answer questions about group means. And it all comes down to the fact that we don't know what the distribution of the individual data is, while we do know what the sampling distribution is. So let me get to that. We are getting close. We've got a couple more things. This one, the law of large numbers. So the center of the sampling distribution, so we said the middle of the sampling distribution we'll call mu sub x bar, and that is the mean of the sample means. That is the same as the center of the individual distribution. So the center of the individual, the mean of the individuals, we called mu. So notice these are two different quantities, and I'm going to demonstrate them as such. Mu sub x bar is going to be the mean of that distribution of sample means, or the mean of the sampling distribution. And mu is, without the sub x bar, is going to represent the mean of our original data. And again, I want to call out these are two different quantities. One is the original data on individuals. One is that new distribution we made by taking these groups of size 100, finding the average height, and then using that as a single data point, the mean of the height for group 1. And then we took a different group of 100, calculated a different mean height. That's the mean of group 2. took a different group of 100, calculated a different mean height. That's the mean of group 3. Then we took all of these means, and we kept doing it over and over and over again. We took all of these means, and we made them into their distribution. That's the sampling distribution. So mu sub x bar and all of my other statistics sub x bar are referring to that one, the distribution of those means, not the distribution of the individuals. That original data. So here we're saying the distribution of the means and the distribution of the individuals are both going to have the same middle, the same average value. What's interesting though, and we kind of thought about this earlier, as the sample size n increases, the sample estimates, that is our x bar where we're trying to guess at the population value of mu, gets closer and closer to the population value. So again, we talked about this earlier when I mentioned, hey, if we took a sample of size 2 and we calculated the mean, and a sample of size 2 and calculated the mean, we can pretty clearly see that those are different. And if we increase those sample sizes, now we take a sample of size 10 and calculate the mean, and a sample of size 10 and calculate the mean. Those are still different, but we might expect those to be closer. Then a sample of size 100 and we calculate the mean, and a sample of size 100 and we calculate the mean. Well, I mean, we might think that those are close enough to almost be the same because there's so many people in each group that kind of everybody will be randomly represented. And certainly if we take a sample of size 1,000 in each group and 1,000 in each group, we're getting closer and closer together. All that this law of large numbers is saying is that as we get more and more individuals in the sample, our sample estimates get more and more accurate. That is, there's less and less variability here. Now, this is a really, really important intuition. So take a moment, pause the video if it doesn't make sense, and really think about this. Because as our sample size increases, again, the sample estimates get less and less variable. They get closer and closer to this population value. They get more and more accurate. That is, again, if we look at groups of size 2, there might be groups of size 2 with really large average heights and groups of size 2 with really small average heights. But if we look at groups of size 100, that's going to even out, and there's not going to be as much variability. If we look at groups of size 1,000, that's going to even out even more. This has kind of an interesting corollary, and ultimately what we're trying to get at is what is the variability of this sampling distribution? Because if the sample means get closer to the population value as our sample size increases, that is, if they vary less, well, then the variance is getting smaller as our sample size increases. Ultimately, what this means is that the variance isn't constant across sample size. The variance is smaller, our guesses get more precise as sample size increases. What this means in equation form, and this is an important thing to understand, is that the variance, or excuse me, I'm missing a squared here, I apologize, that the variance of the sampling distribution is not the variance that we observe in our data. And the reason is because, again, as the sample size increases, this variance gets smaller and smaller and smaller. It is related to the variability in our data. That is, if the data are really variable, if there's some people with really tall heights and some people with really small heights, then the mean of those groups is going to vary more and more, versus if everybody just had the same height, then the means are all just going to have that same height too. So it's related, but it's also in some way related to sample size. Ultimately, how the variability of this, or the variability of these means is related to sample size, and the original variability of the data is that the variability of the means is the original variability of the data divided by the sample size. And note that divided by the sample size means that as the sample size increases, this number gets smaller. So let's say the original variability is 10. If the sample size is 1, then the variability stays at 10. If the sample size is 10, or excuse me, if the sample size is 2, the variability drops down to 5. If the sample size is 10, the variability drops down to 1. If the sample size is 100, the variability drops down to 0.1. So as the sample size gets bigger and bigger and bigger, it makes the variability of the means get smaller. That is, the means get closer and closer together as the sample size increases. Now, this is all written in variance form right now, but we can also write it in standard deviation form. We just take the square root. So the standard deviation of the sample means is the square root of the original. Oh my gosh, I'm just messing all this up here. I apologize. Let me get my pen out. I need my squared there too. I apologize, team. The variability or the standard deviation of the sample means is the square root of the original. Oh man, this is terrible. Well, sorry. We're just going to have to deal with it. Let's do it like this. This is the common way I like to write it. Sigma over the square root of n. I put the square root on the wrong thing. That's what's going on here. Is the original standard deviation divided by the square root of n. So I just take the square root of this whole side. The square root cancels out with the squared, and the square root's left on the n. So again, the original standard deviation of the sample means is the original standard deviation of the data divided by the square root of n. So this also, again, is taking into account the fact that as the sample gets larger, the variability, and in this case, the standard deviation, which is another measure of spread, gets smaller and smaller and smaller. All right. So now we get to move on to the central limit theorem. So we've been looking at all of the kind of fundamental pieces, but the central limit theorem is where we're going to really put all of these together. The central limit theorem says that the distribution of the standardized sample means will be the standard normal distribution for a large sample size. Now, again, the distribution of the original data doesn't change. This is for the distribution of the sample means. And note what we're adding. We're adding the distributional component. We knew from that law of large numbers what the mean and standard deviation was for the sampling distribution, but we didn't know what the distribution of that looked like. That is, we didn't have the equation. That's what we didn't have. We didn't have the equation. And the equation is actually a very important component. So the central limit theorem says we can describe the sampling distribution with that standard normal equation. Again, it's not really the math that's as important here as to what this adds to the flow of what we're doing. So take a moment to kind of pause and reflect on what we've done to get to this point. We started by saying we're going to use a sample to guess at the population, but we know the sample value is going to be wrong. So we're going to use one of these inferential methods to account for this error in some way. Dr. Florin promised that we can do this, but we can only do this if we know the distribution, again, or the equation that the population follows. We learned that from the law of large numbers, we can get the mean and standard deviation from the sampling distribution. Again, that's the population as it relates to group means. And now what we're adding is that the sampling distribution is normally distributed. That is, we have an equation for large n. And that this isn't just made up, this is mathematically demonstrated. So this is a very important addition to what we've had before. And actually, you know, I made a little app to demonstrate this. So let me go on and pull this up so that we can look and see what this looks like in practice. So here's our little app. You can actually click the link in the PowerPoint, or you can just go to this website on your own if you'd like, where we have what the original individual data looks like, and then we have what the sampling means look like if I took samples of size blank. So earlier we were talking about samples of size 100. And on this app, we see that if the individuals look normally distributed, my sample means will also look normally distributed. That's not particularly interesting. Let's pick a different distribution that our individuals follow. I'll pick the exponential distribution, which looks pretty non-normally distributed. So let's say I'm studying a particular context and my data values come and I plot them and my individual data values look like this. This does not look normally distributed whatsoever. What's fascinating here is that with a sample size of 100, if I took 100 people and then calculated their mean, 100 of these people, most of them are probably going to be down here, very few up here, but I picked 100 anyway. Picked 100 people, and I calculated their mean value. And then I did it again, 100 people, calculate their mean value, and then I took all of those means and I put them on a graph. This is what that graph would look like. And isn't that interesting that this graph looks normally distributed? Now let's say I just took samples of size 2 instead of size 100. What you'll see is that samples of size 2 don't look particularly normally distributed. Let's try a sample of size 10. Well, that looks better, but it still doesn't look particularly normally distributed. Let's try a sample of size 30. Well, that's looking better, still a little bit of an upper tail here. 50. 50 looks pretty normal to me. And again, when we get up to size 100, it looks pretty darn normally distributed. That is, it has that bell shape of a normal distribution. Again, this is fascinating because the individuals look like this. It doesn't matter what sample size of individuals we have, the individual data is still going to look like this. What the central limit theorem says is if I look at the sampling distribution, that is the means of sample sizes of 100, then that sampling distribution is going to look like a normal distribution. And I can use this normal distribution equation if I'm studying group means. Note that there's nothing that I can really use if I'm studying the individuals because I don't have the equation for whatever this looks like. But if I'm studying group means, I can use the normal distribution equation that we actually wrote earlier in our lecture. Now, don't worry, we're not actually going to use that equation. We'll have software do it for us, but we can. All right, so let's write out a bit of the equation form of what we just learned, the simpler version of the equations. So we're going to start with the basic standardization notation. I'll note that I'm doing this with the sample means, not individual data points. And as we just discussed, and I hope you're hearing hit home over and over again, this doesn't work with individual data points. It just works for sample means. And another thing, as we kind of just explored, it only works for large sample sizes. The formal proof is as n approaches infinity. So as n gets very, very big. But we just saw that practically samples of size 30 or 50 or 100 for sure start to look very, very normal, even for distributions that are not particularly normal looking for the individuals. The means will look normally distributed. All right, so we start with this, the basic standardization notation. Now we add in the values calculated from the sample individual data. So this is our plugging in for the mean of the sampling distribution. We said the mean of the sampling distribution was the mean of the individual data. We said the standard deviation of the sampling distribution was the standard deviation of the individual data divided by the square root of n. So we're just plugging this in, writing that out. And this is what we got from the law of large numbers. Now what we're saying through the central limit theorem is that this quantity, the standardized sample mean, is distributed as a normal distribution with a mean of 0 and a variance of 1. That is, it's distributed as a standard normal distribution. And that's the contribution of the central limit theorem, this last component here, that this quantity is distributed as a standard normal. Again, it's not just saying that it's normally distributed. We now know which of those infinite normal distributions it is. It's the standard normal curve, and we have the equation. Incidentally, this also kind of implies that the sample mean is distributed as a normal distribution with a mean of mu and a variance of sigma squared over n. So this kind of works too, that we know the distribution of sample means. We'll lean more heavily on this in this class, but both of these are true. And gosh, if you can read that, well, good for you. I'll just say it is very difficult to draw things out on the mouse. I really, really, really suck at it. So sorry. That's why I type out all our equations in this class, so y'all don't have to deal with that. You should see my my regular handwriting. All right, so what's the utility of this? Well, recall that the biggest, most sketchy process of the whole inferential statistics thing is where I said, look, if we know the equation, the population values follow, then we can do the rest. That seemed completely arbitrary, because how are we possibly going to get the equation that the population values follow? We're just going to make it up? And the cool thing about the central limit theorem is it says that we know what the distribution of the population for the group means are. Now, I can't say this enough. Nothing's going to tell us what the distribution of those original data values are. We can make a guess. We can make an educated guess. But that's about as sketchy as you would think. That's where the sketchiness comes in, as you think of just kind of making up a distribution for individual data values. And though we could potentially argue it is that's sketchy. That's the original sketchiness you probably looked at this with. The cool part is that often we care about group averages. And if we're looking at group averages, and if we take large enough samples, and large enough depends on who you ask. Some people say above 30, some people say above 50, some people say above 100. But if you take large enough samples, the central limit theorem provides a mathematical proof as to what the equation is that the population group means follow, or that those group means follow, the sample group means follow. And that is how we can use a distribution for the population, is that we use the sampling distribution, not the distribution of the original data. And with a sufficient sample size, the sampling distribution is something that we know for sure, no matter what the original data look like. And that's the coolest part, that with a large enough sample size, it doesn't matter what the distribution of the individual data are. And in that example, we kind of explored that I could pull a distribution that looked very non-normal, a very crazy looking distribution of individual data, where you might look at that and say, we could never come up with an equation that measures what the population looks like in this case. And the truth is, you'd be right. I might never be able to come up with that equation. Potentially you couldn't either. But even in that crazy circumstance, if we stop talking about individuals and start talking about group means, then we can use some math in the form of the central limit theorem to get the equation that the population of group means looks like. And then we can make do the process of inferential statistics with these group means. This clearly represents a massive advancement in the field of statistics, because without this, we'd simply have to guess what the population distribution is. And again, the degree to which we guess wrong inadvertently increases our error, and we'd never know how much error it would increase. We might have that alpha. Remember, alpha is the proportional measure of error, the decimal form. We might say we're comfortable with 10% error on this decision, or in this confidence interval, we're comfortable with 10% error. But if we guess the distribution wrong, that error would increase, and we would never know. But again, this, as cool as it is, only applies to when we're studying the sampling distribution, and that ultimately means it only applies to group means with large groups, large enough for that central limit theorem to kick in. Sometimes with data sets with very big outliers, we need an extraordinarily large sample, so this isn't the best approach. But for most situations, this works pretty well and is pretty cool. All right, well, in the next video, we're going to get started practicing utilizing this. We'll go over a couple of basic points, and then we'll jump into the process of hypothesis testing and creating confidence intervals using some of the stuff that we've discussed in this video.